I'm really excited to introduce our speaker for this afternoon. Jennifer Wiseman is an American astronomer, received her bachelor's degrees from MIT, her PhD in astronomy. She's currently a senior astrophysicist at the NASA Goddard Space Flight Center, and she is the senior project scientist for the Hubble Space Telescope. She studies mostly star-forming regions of our galaxy using radio-optical and infrared telescopes, and has a particular interest in molecular cloud cores, protostars, and outflows. She also has an interest in science policy and public science outreach. She served as a Congressional Science Fellow of the American Physical Society, an elected counselor of the American Astronomical Society, and a public dialogue leader for the IIAS, the American Association for the Advancement of Science. She also is director of the IIAS-sponsored Dialogue on Science, Ethics, and Religion, the DOZER program. She appears in science and news venues, including the New York Times, the Washington Post, Nova, and National Public Radio. What she's going to talk to us about today is A Magnificent Universe, a Contemplation of Human Purpose. Jennifer, please take it over.
Thank you so very much. I'm so honored to join you today. Thank you, Gail. Thank you, Maynard. Thank you for all from IRAS who have supported this event. And thank you all in the audience for joining us. There was a little confusion in the title, but my title is actually going to be about a universe leading to life and what we're observing in the universe that is incredibly interesting, and how the universe has developed and become more complex over time, leading to life. And that does beg these questions, these bigger questions of not only awe and inspiration, but also purpose and things that are beyond science alone, that people are inspired to ask. And so I want to get into that right away. And we are not discussing this under the umbrella of any particular organization. I'm not representing NASA or any organization like that I work for tonight. I'm just sharing with you some of my own personal perspectives, and I hope you'll share back some of yours when we get to the discussion time. So I'm going to see if we can look at my shared screen here. All right. This is what we have to cover in just a little bit of time here tonight. A universe leading to life, and the bigger questions that this can inspire, and reactions of awe, questions of purpose, feelings of inspiration, I hope. So we are privileged in the day and age that we're in, because we have magnificent professional telescopes on the ground and in space that can give us images like this that show us stars forming in these vast interstellar clouds, these active regions of stellar birth, and young stars then are energetic enough, if they're massive enough, to shine back light on the surrounding gas out of which they formed and ionize it, which lights it up into these beautiful colors. We can see the activity. We can see things which I will be sharing with you deep in the universe, thanks to the professional telescopes that we now enjoy. And it's a bit ironic, because at the same time, we've light polluted ourselves out of being able to see the night sky most of the time from our backyards. And it is too bad, because it's really throughout human history, that contemplation of just looking at the night sky with the naked eye that has inspired so much reflection, whether that's through religion or philosophy, or even inspiring music and art. And now most people in the world live in areas where the night sky is lost in the glow of our city lights. And that is unfortunate. It's not necessary. We can dome the lights in our cities and get just as much light as we need on the ground for safety without polluting our night sky. But we can see things terrifically with telescopes, professional telescopes, and we are enjoying what we're learning from these. And these observations are inspiring those deeper questions yet today. We use different kinds of telescopes. So here's just an example, some examples. We have telescopes in space. So the most famous one there is on top, the Hubble Space Telescope, which is a satellite about the size of a school bus, and it's in orbit right now around planet Earth. It's moving very fast, over 17,000 miles an hour, but it has very stable pointing. So even though it's moving very quickly in low Earth orbit, it can keep stably pointed on distant planets or galaxies and transmit back the observations to the ground. The reason we put telescopes in space, and by the way, there have been and are quite a few telescopes in space with different capabilities, is to get them above the Earth's atmosphere. So you can see the Earth kind of below the Hubble telescope there, and the clouds and the other components of the atmosphere can blur the images that you would otherwise get, and can even filter out some of the light, the kinds of light that you would want to receive, like ultraviolet light. And so putting telescopes high on a mountain, or even better, putting them in orbit above the atmosphere is a wonderful revolution in getting clarity from the deep universe and imaging it. But we also still get very complementary and good data from telescopes on the ground. And so the lower left is an example of that. Those are the Keck telescopes on the top of the volcano that we hope is dormant in Hawaii. And the lower right are the ALMA radio dishes that receive millimeter and submillimeter wavelength radiation that often is emitted from these deep interstellar clouds or distant galaxies. Every telescope has its own little niche of what kinds of light it can see, whether it's visible light or radio waves or X-rays. And every telescope has a different niche in terms of its field of view, how much of the night sky it's taking in at the same time, how much clarity and sharpness it gets, how much detail, and how long it can be used to do certain observations. So we use all these different tools in kind of like a symphony orchestra fashion to pull in different parts of the music in order to get the full picture, the full musical piece, or the full, in this case, the fuller astronomical understanding of what we're trying to study, whether it's a galaxy or the interstellar medium, gas and dust, or planets. And I myself have used all these kinds of telescopes. I've used the telescopes in space, I've used optical and infrared telescopes on the ground, and I've used mostly radio telescopes on the ground to study star formation in interstellar clouds. And I've used all this information together. So here's an example of what you can get when you get real clarity. So this is a really dense star cluster. This is a globular cluster near the middle of our Milky Way. And the stars are very close together, at least 4 times, and maybe more so closer together than our sun is from our nearest star in our neighborhood. If you were to look at this cluster with most telescopes from the ground, the light would all kind of blur together. But if you can get that sharp resolution from being above the clouds, and this was taken with the Hubble Space Telescope, you can differentiate star from star, even in a crowded field, and see that stars are different, that star differs from star in splendor. That's a biblical verse, by the way, so you get extra credit if you can find it. And really, we can learn that stars are not all the same. You see their different colors here representing different temperatures. And their surfaces of the stars. Stars have different masses and compositions and histories. And we are getting spoiled with these space images. Here's an image released last year at the 30th birthday of the Hubble telescope, showcasing a region of star formation in the little sister galaxy to the Milky Way. That little galaxy is called the Large Magellanic Cloud. And here within that little galaxy is a region of active star formation in the Red Nebula at the top, and one single massive star that has episodic eruptions, which is the donut-like thing in the lower left. So it shows us that our universe is very active, and with tools like these major professional telescopes, we can learn things that we've never known before. So I'm going to do a little show and tell of some of the neat new things that we've learned with these telescopes, especially in the last few years, and then take the next step of talking about what we've learned about the universe developing over time. So here's some of the just show and tell of cool things that we're discovering in the universe in recent years. One is that we've discovered what had been predicted by folks like Einstein and others, is that radiation is not the only way that information can be transported across the universe. There can also be distortions in space-time. And that can happen if you have accelerations of mass. And as in particular, if you have accelerations of gigantic masses in space, deep space, that can create a detectable traveling distortion of space-time. And this was first detected a few years ago for real, after years and years of trying from ground detectors, including the LIGO facility on the ground. And now there are others around the world that are testing just tiny changes in the distances between objects in their detectors that change if a distortion of space itself travels through the detector. And that's what the signal is on the right there, is a tiny distortion in space-time that traveled through the LIGO detector, was picked up, and was determined to be a merger of, the origin must have been from a merger of black holes deep in the universe. And that's what that simulation is on the left side. The signature was exactly what was predicted from theory and computer simulations from years ago. And so now more of these events have been detected, and we're learning much more about the fate of massive objects in the universe, especially when they come to the closure of their active period of what we might call life, although they're not alive, and create a merger that can create that acceleration that distorts space-time. You may have seen that we've recently imaged a black hole. Now, of course, black holes don't shine light. That's why they're called black holes. Not even light can escape from within the critical radius of a black hole. But right around that critical radius, material can accrete onto an accretion disk and orbit the region, and that can be a very bright and active region. And so this is an image created from using a whole array of telescopes on the ground to really pick up that radiation coming right around the radius of a black hole and image it. And it's very, very exciting to see this accomplished. Closer to home, we've got rovers roving around on Mars, like Curiosity, Perseverance. These rovers are getting more and more sophisticated, taking images. Here's the first Perseverance image from the surface of Mars. So sending probes is often the first way we can explore more deeply the planets and moons in our own solar system. And of course, humans may, in the not too distant future, be going beyond the moon to explore places like Mars in person. We're even studying things coming through our solar system that did not originate in our solar system. So here's an artist's conception of an object called Oumuamua, which is an asteroid-like thing that was discovered whizzing through the solar system, but it had a trajectory that indicated it did not originate from the outer parts of our solar system, like all the other asteroids and comets that we know of have come from. This came from some other star system. It was ejected through interactions in that star system. And we've since discovered a comet with also an interstellar trajectory, Comet Borisov. So by studying these objects and their compositions, we're starting to study the makeup of other star systems by looking at actual material created in those systems. And that's very exciting as well. This is the cockpit from the latest space shuttle mission that went to service the Hubble telescope back in 2009. We don't have the space shuttle operating anymore, but fortunately that crew did a wonderful job of putting in new instruments and repairing the older ones on Hubble. So the Hubble telescope is in great shape. But one of the astronauts, John Grunsfeld, took with him on his space shuttle trip to Hubble a special item. So here's I keep saying this is the cockpit, but I think it's actually another part of the pressurized part of the space shuttle. And looking out the back window there, you can see the Hubble telescope as it was being serviced in orbit. But in front is a replica of Galileo's telescope. And astronaut John Grunsfeld brought this replica up and tried it out. He said it really wasn't very good, so he was amazed that Galileo could see much at all. But this shows you the juxtaposition that in the last 4 centuries, between Galileo's use of the telescope to make recorded observations of the heavens, and now the observations that observatories like Hubble are doing, we've had an enormous increase in technological sophistication. And that gives us a lot more information about the universe. And that then, of course, feeds the deeper questions that we have about the universe. What we've learned through our observations is that the universe that we live in is beautiful, it's active, it's enormous, and it's progressive. And here I'm talking not necessarily about a political stance, but about a change over time, an evolutionary stance. And I don't have time tonight, unfortunately, to go in great detail about all these things, but I will a little bit. So here's one of my favorite beauty shots of the universe. It's another cluster of massive stars in our own galaxy recently formed, and the winds from those stars are carving out these pillar-like structures in the surrounding leftover gas as it blows it away. And also the radiation is lighting up that gas and ionizing it so we can see it. So when astronomers see places like this, we say, oh, it's beautiful. And we also say, oh, this shows us that the universe is active. Stars are still forming. We also, I hope, will pause to recognize that we do live in an incredible universe that inspires wonder and awe. And in fact, we're not the first to think about this. Kant is quoted as saying this, and I think this is also translated from something on his tombstone. He said 2 things continued to fill his mind with ever increasing wonder and awe the more often and intensely he reflected on them: the starry heavens above him and the moral law within him. And I think that is interesting today. We are still contemplating the heavens and, in fact, the natural world in general, as well as contemplating the deeper questions of justice and morality within us and within our culture. All right, so here's an image from a telescope on the ground of the Orion region, near and dear to my heart. I studied this for my doctoral thesis years ago. And if you look more closely at one of these nebulous regions in the Orion constellation, you see a fuzzy region that's a little reddened. And if we look at that region with the Hubble Space Telescope, you don't see this big field of view with all the other stars, but you see more detail around that one little region that you might think is one star, but it turns out to be a whole cluster of stars. So blown up, you see the Orion Nebula in all its glory. Again, one of these massive star forming regions where stars have recently formed. There's a dark region behind it where stars have not turned on yet, but you can see it. You can see these protostars with radio telescopes. And if you look closely at some of the littler stars that you might not have noticed first on and expand them, as I've done here, you can see these dark regions around these little stellar objects. These are dusty disks. One of them you see there is kind of a face-on orientation. One is in kind of an edge-on orientation. These disks have the diameter that's approximately equal to our solar system's diameter. So one of the things we've learned in recent years is that stars in our era almost all form with these dusty disks around them. And it's in these regions where planets coalesce, planets form along with their parent stars. And in fact, we've learned in the last couple of decades, little more than that, but in recent human history, let's say, since I started graduate school, that there are planets outside of our solar system. And in fact, planets are common orbiting other stars. So that is also a very exciting recent development. On the other end of the stellar lifetime, stars, after they run out of their nominal hydrogen fuel in their cores, they start to become unstable. They can release their outer atmospheres, and eventually the bigger ones actually explode in supernovae. These releases of material back into the interstellar medium actually seed that interstellar medium with heavier elements that are forged inside the star. As the star is normally shining, there's a process of fusion going on that's creating from the hydrogen that's most of the makeup of the star, but forging heavier things beyond helium, even things like carbon, oxygen, nitrogen, iron, things that we need for solids and to support life These materials then get expelled back into the interstellar medium, and then they're caught up in the next generation of stars and their planets that form. So we know that our own sun and solar system, our sun is not a first generation star. We needed previous generations of stars to create the heavier elements that we now have in our own sun, and that enabled planets like our Earth to form in our own solar system. Here's an artist's conception of another star with planets, but it's a real system discovered by the Kepler telescope. Most of these exoplanets, as we call them, planets outside our solar system, have been discovered through indirect techniques, where we see the star and we see it dimming in very periodic fashions as its planets transit in front of the star in the orbit. And we can learn a lot from those transits as well, including some of the composition information about those parent stars. Stars and these nebulae fill up galaxies. So galaxies like this can contain hundreds of billions of stars and their planets, as well as these beautiful nebulae where stars are still forming. This galaxy has so many stars in its core that all the light just kind of blends together. I think it's beautiful. Some of them take on this spiral structure over time. If you look carefully, you can see background galaxies as well in this lovely image of galaxy NGC 1309, poetic name. We cannot get far enough out of our own Milky Way galaxy to take an image, to take a selfie. So we have to look around from our own position and get a good idea just from looking around. And this is an artist's conception of what we think is our own galaxy Milky Way looks like. You'll see our solar system down in the lower part of this image, our sun, the planets we're on, close to what we call the local arm or the Orion arm. There are other arms. We can look toward the center of our galaxy and see a lot of stars. We can look off of the plane of the galaxy and see many fewer stars. And we now know since the last century that there are other galaxies. This was an argument of debate about a century ago, but that was finally resolved thanks to telescopes, that there are many other galaxies. Here's a couple. One of them we're looking at face on the right, one edge on the left, where you can see how much dust and gas are in these spiral type galaxies. And in fact, if you look in ultraviolet light, which these images include, you can see a lot of those bright hot spots in sections of these galaxies and in their arms where these nebulae are lighting up because new stars are forming and lighting up the surrounding dust and gas. Just beautiful. We've also learned through deep space imaging that galaxies interact with each other, especially in the earlier universe. Before the universe had expanded to the point where it's expanded today. And galaxies, while they tend to be caught up in this expansion and move away from each other, if they're close enough to each other, their mutual gravitational tug will dominate and the galaxies will pull together and merge. Now, these mergers seem to be common in the early universe, and we can now tell that our own galaxy is the product of previous mergers. They get bigger with merging. If you think you're safe from this, we now know that our Milky Way is on a direct collision course for a future merger with the Andromeda galaxy in a few billion years. So get ready for that. But simulations tell us that most of the action when this happens is simply distortion of the shapes of these galaxies. There's still a lot of empty space, so very few star-to-star collisions. But the interactions, such as in this pair, can stir up turbulence, which can stir up a lot of active star formation, a lot of collapse of these little gas clouds into collapsed modules that become stars. And so you see those bright hot spots where stars are induced to form by the merger here of the antennae galaxies. Just beautiful, spectacular activity. So we know galaxies have built up in mass over time through mergers, and keep in mind that most of the mass in these galaxies is not seen. It's in what we call dark matter, but it has a lot of effects. And as we think about the number of galaxies, we've learned that the universe is enormous in both space and time and content, I would say. So here's our sample galaxy here, but we now know there are hundreds of billions of these galaxies. And of course, one of the most famous images, my favorite, is the Hubble ultra deep field, which is the product of just taking the Hubble telescope and pointing it in a direction of space that didn't have many nearby stars to drown out the image, and just collecting faint light for days and days to see what would show up. And in the resulting image, what showed up are thousands of these little smudges of light. Now, these little smudges are not stars. There's a couple of foreground stars in here from our own galaxy, but the vast majority, even of these tiny little specks of light, are other galaxies that can contain billions or hundreds of billions of stars. And this is just a little area like looking through a soda straw or something, a little area of the sky. Imagine this extrapolated over the whole sky, and that's the kind of universe that we live in. It's really mind-boggling. If we could get far enough away and look back, our own Milky Way would be like one of these spiral structures up in the upper or the left side of this image. And then if we assume that these other galaxies have plentiful planets around their stars, like we now believe is true for the stars in our own galaxy, we're talking about planets, hundreds of billions of planets in these galaxies. So it is really, really mind-boggling and mathematically challenging to contemplate the enormity of the universe. And of course, these galaxies are shining to us from different distances. So we're seeing them at all the same time in this image, but the light started its journey to us at vastly different times. The nearer galaxies, we're seeing them as they were, but we're seeing them as they were closer to us in time. The more distant galaxies, we're seeing them as they were farther back in time when that light began its journey to us. Some of that light becomes reddened on its journey to us because it's passing through space-time that is expanding as it travels through that space to get to us, and the light becomes reddened during that transit. And so what we have learned as we very carefully discern the different distances to these galaxies is that galaxies were not the same in the early universe as they are now. So here's just a little fun animation of traveling kind of into this deep field, where you can see as we kind of travel through that the nearer galaxies, some of them have this beautiful spiral structure. They've had time over billions of years of cosmic history to merge and become more massive. They've had generations of stars come and go to bring in more advanced elements into their stars and planetary systems. As we move to these more distant galaxies, we're looking at galaxies as they were millions and now even billions of years back in time toward the beginning of the universe. And you see they are smaller. They haven't had time to develop that spiral structure. They haven't merged yet as much. So they're ratty, they're smaller, they're not as mature, and we don't see as many of them. It doesn't mean that there aren't as many, but we're just not seeing as many in this Hubble image because the light has been shifted so far into the red, into the infrared part of the spectrum, that the Hubble telescope can't even pick them up. So here's a pictorial of taking out these galaxies from this background image and then lining them up according to their distances. So the nearer by ones are in the circles on the left, and the more distant ones closer to the beginning of the universe, we're seeing the light from them, are on the right in those circles. So you can see going from the right to the left that galaxies have changed over time. They've become bigger as they've merged. They've developed more complex and structures and ordered structures. If you do spectroscopic analysis, you see that the composition of galaxies grows more complex over time because the generations of stars within them produce heavier elements like carbon, oxygen, nitrogen, silicon, even more complex things through supernovae explosions that enable solids like planets to form in subsequent generations of stars, and even life to be sustained on at least one planet in our Milky Way. Here's another way of looking at this. The telescopes on the left represent our current epoch of time, and from top to bottom, how our instruments have gotten more sensitive over time. Some examples from ground-based telescopes and different cameras in space, and the Webb telescope at the bottom that's due to launch in December of this year. And as those cameras get more sensitive, we're able to see fainter and fainter objects in space, including faint galaxies. So that enables us to see farther back into space, which means farther back in time. That's what those arrows are depicting. And on the bottom, you actually see, not in a linear scale, time going from right to left. So the beginning of the universe would be off to the right, the Big Bang, and then we're seeing galaxies as we go from right to left, and as they mature, the galaxies more toward the left of this image have had time to take on that big spiral structure like our Milky Way has. The galaxies that we're seeing farther out in space, where the arrows go farther to the right, are baby galaxies. They've just been forming. And we can now see some of those, and the Webb telescope will be able to pick up even those highly redshifted galaxies that Hubble cannot see, that are even farther back in time, these proto-galaxies just starting to form from early collections of the first stars and gas out of which they formed, coalescing due to gravitational pull. So we believe the universe is about 13.8 billion years old, and we're now seeing back to within the first 0.8 of the 13.8 billion year history of the universe. And we're able to see how the universe has changed over time by looking with our time machines, our telescopes, and seeing the change in galaxies and their content over time. So we can confidently say that the universe has developed over billions of years of time, and it continues to mature and change with the production of stars within these hundreds of billions of galaxies in the observable universe, and those stars producing heavier elements, which enable planets to form around stars, and even providing conditions for life to exist and thrive on at least one planet. We see the universe moving in this direction. So does that imply that the universe has a purpose? All right, so I have just jumped from the science, which is pretty much the consensus scientific view amongst astrophysicists these days, to a question that is outside of scientific experiment. The question is a philosophical one. It can even be a theological one. Is there a purpose for all of this? Do the observations more support a philosophical conclusion of purpose, or do they more support no such thing? Or can you even ask such a question in the age of science, as IRAS is titled? So let me explore this a little bit. One way of looking at this is this response, which the late Steven Weinberg said, that the more the universe seems comprehensible, the more it also seems pointless. And all these statements I'm going to show you, I'm not evaluating them as correct or incorrect. No one can. These are personal perspectives, and this one is certainly a valid one could come to, because while the universe seems to have matured toward the point of supporting life that can reflect on itself, like we're doing right now. But then as we look to the distant future, we already know we've passed the peak of star formation history in our universe. We're on the downside of star formation activity. We've still got quite a few billions of years to go, but star formation has already peaked. Eventually, if you just kind of run the tape forward, the universe appears to be expanding so much that it will cool and eventually die out. So is that all there is? Is there any point to this? And some people would say maybe not. Now, of course, we're often making very new discoveries about the universe, such as dark energy and things like that may provide a very different fate for the universe. And there are theological positions which would say that this is not pointless, and there is, in fact, a very hopeful future. But this is one reaction, and it's certainly a valid reaction to looking at this. I like the question that the Templeton Foundation posed quite a few years ago, but I keep pulling this up, to some scholars, theologians, historians, scientists, historians around the world, and just ask them this question: does the universe have a purpose? Now, these scholars all would pretty much agree with the scientific picture I just told you about the history and development of the universe, but they obviously do not agree with this philosophical question: does the universe have a purpose? Here's some of the one-word answers from some people. You may recognize their names. If you go to bigquestions.org or to the archive, you may have to search around a little bit. This is getting kind of dated, but you can see their one-page essays answers, which are quite interesting, where they explain why they've answered the way they have. Scientist Professor Atkins said no to the question, does the universe have a purpose? He says, in the absence of evidence, the only reason to suppose that it does is sentimental wishful thinking, which underlies all religion, an unreliable tool for the discovery of truth of any kind. So a pretty strong response there. From Professor John Hott in the US, he says, yes, the fact that we can even ask such a question as to whether the universe has a purpose at all suggests an affirmative answer. The fact that we're even having this conversation tonight. He says the impassioned search for meaning, perhaps our species' most distinctive trait, is not a longing that somehow lifts us out of the universe or that takes place outside of nature. We're, after all, as much a part of nature as roaches and rivers, and so too is our thirst for meaning. So if we accept evolution, as indeed we must, our longing for meaning is nature, in the same sense that birdsong and the howling of wolves are nature. And Jane Goodall says, certainly. She said, of course, science typically scoffs at any belief in a God and tells us that we have a God gene and that the tendency toward religious belief is simply part of our biological makeup, as inevitable as the universal human smile. And yet, even if this were so, we would still have to ask why. Why should we be programmed to believe in a God? Why are the laws of physics designed to make life ever more complex? And where did those laws come from? That was her take on it. And I would commend to you this book from biologist, Professor Dr. Dennis Alexander, the emeritus director of the Faraday Institute for Science and Religion in the UK, who's written a book called Is There Purpose in Biology, which I think is a worthwhile read. Part of this discussion has to do with avoiding minimalizing things or simplifying things too much. The reductionism that has often made these questions seem out of bounds. And I'm not the first one to coin the term nothing buttery, but we need to be careful that we don't fall into the trap that a scientific explanation for a natural phenomenon, including our behavior, is the whole story. In fact, this nothing buttery can sound like things that say we are nothing but our chemical makeup, we are nothing but our genes, we are nothing but our neurological makeup. Everything can be explained and reduced. And it turns out we're learning more and more that this is just not the case to describe reality in our lived experience. Can we bring theology into a discussion of what we've found from science? Of course, these are different things. Science is looking at measurable results from observations of the natural world. Theology is asking bigger, deeper kinds of questions, but I think they can be complementary. The late Sir John Polkinghorne said that science and theology are both concerned with the search for truth. In consequence, they complement each other rather than contrast one another. Of course, the two disciplines focus on different dimensions of truth, but they share a common conviction that there is truth to be sought. I think that's really very important. And Dr. Nancy Edelman at Catholic University says scientists and people of faith, she was referring to, speak a common language, which is awe and wonder about the world at large. Let's meet on common ground and consider our common interest. All right, so if we're going to talk about purpose, I think I have to touch a little bit on significance, because people put those together sometimes. They look at the universe and they say, wow, the universe is so amazingly old and it's so amazingly huge that must mean that our lives are insignificant. In fact, I had this reaction the other day. I went to one of the medical professionals that I visit, and we got to talking and told him that I study the universe, I study astronomy, and usually the reaction I get is, "Oh, wow, that's cool. Tell me more about what you're discovering." And he said, "Oh, don't tell me more, because when I hear more about the universe, it just makes me feel like our lives are so pointless and meaningless. It just blows my mind, and I just don't want to hear it anymore. It's too depressing." So, so do we need to have this sense of insignificance and purposelessness when we look at the universe? I don't have time now to go into all the history here, but some of this, it depends on the time frame that the question is being asked. We all know that the usual framing of the Copernican story, that finding out that the Earth is not in the center of the solar system demoted us and made us realize our insignificance. But I commend to you Dr. Dennis Danielson, a professor of literature, who wrote an article some years back in Physics Today, or sorry, in the American Journal of Physics, and also Dr. Singham in Physics Today, about how back in Copernican times, actually being in the middle of something was bad. That's where hell is. You want it to be elevated outside of that. So we have to be careful not to read into yesterday's history what today's interpretations might be. But nevertheless, the significance, is it based on whether you're common or rare? Is it based on whether you're in the center or not? That's a philosophical perspective. And if we find life beyond, I mean, we now know, of course, the Earth is not in the center of the solar system is not in the center of the galaxy is not in the center of the universe, there might be a multiverse. Does that mean we're insignificant? And if we find life beyond Earth, does that also mean that Earth-based life becomes less significant or more? You know, this is a philosophical choice, and it feeds into our understanding of purpose as well. Jill Tarter points out that we are actually connected to the universe. We're not just external observers. We are actually physically connected. She says, we're made of stardust. The iron in the molecules in your blood and your hand came from a star that blew up 8 billion years ago. The iron in your left hand came from another star. We are the laws of chemistry and physics as they've played out here on Earth. And we're now learning that planets are as common as stars. Most stars, as it turns out, have planets. So I think this is really cool. We're not just observing a universe, we're actually intertwined with the universe. To me, that begs a sense of philosophical significance. I'm going to go through some of this quickly so that we don't run over my time. But I will point out that we're discovering lots of these exoplanets right now, including close by. Here's the closest star system to us, Alpha Centauri. And in that system, the closest actual star to us is this little tiny star called Proxima Centauri. And it has a planet possibly in its habitable zone. So we don't have to look far in that sense relative to the stars in the galaxy to find exoplanets, and maybe being able to do detailed studies and maybe even find out if they are habitable for life. We don't know yet whether there's life beyond Earth, but we're certainly developing the tools now to hone in on whether these exoplanets are habitable, whether they have temperate surfaces, whether they have water. And then also we are developing techniques of developing what we'd call biosignatures, which is looking for the products of biological activity on these exoplanets. If we see those biosignatures, is it going to affect our view of significance of life? We will be looking for evidence of oxygen in these atmospheres, liquid water that could support life, reflected light that might actually be indicative of life. This is what we see when we look back at Earth. We even see methane produced by cattle when we look at Earth. So we might find a bovine planet or something, but we have to rule out other explanations as we start looking at these exoplanets. I'm going to quickly mention that religious thought has thought about this possibility long before our current epoch of finding exoplanets. Islamic thinking is that the Most High has the power to create 1,000 worlds beyond this world. The Catholic Church has been involved in the last few years, especially in astrobiology. The Pontifical Academy of Sciences has held conferences on astrobiology because they believe that the question of whether life exists elsewhere is a very interesting one and deserves serious philosophical and theological consideration. Dr. David Weintraub mentions that Judaism accepts the possibility of extraterrestrial life, in fact, may require it, because you don't want to put limits on the power of the creator, and you don't want to put shackles on God's creative power. So, are we cosmically special? That depends on your philosophical interpretation. Either we are, because life exists here on Earth and may not exist elsewhere. That's the view of astrophysicist Howard Smith, who thinks that the astrophysical evidence is pointing to the idea that life may be quite rare. Even though there's lots of planets, the conditions needed for sustained life may be quite rare. On the other hand, you could react in the sense that if there's life everywhere, that means the universe is robust for life, and we're part of something where life maybe was purposed to be from the very beginning. In Christian thought, which is my own faith, there's also a step of significance in the incarnation, where the God of the universe actually became part of human life on Earth and told us that he has come that we may have life and have it to the full. This is another piece of evidence, not scientific in the sense of measuring with telescopes and microscopes, but a sense of evidence that there might be other reasons to think that life, and even our life, has significance, not based in our physical location or our lifespan, but based on other input that we have. So how do we respond to this information? There are different responses. We can be bewildered, or we can be full of wonder and awe. We can offer praise to God. If you're a person of faith in God, you can even lose faith if you go the other direction and feel so bewildered. You can feel insignificant, or you can feel very grateful that you're significantly part of a universe and being enabled to study and understand the things that we can now see. I hope we're all inspired to curiosity. Here's a famous quote from Blaise Pascal, who was contemplating on what he understood of the natural world of his time. And he said, when I consider the short duration of my life, swallowed up in the eternity before and after, the little space which I fill engulfed in the infinite immensity of spaces of which I'm ignorant and which know me not, I am frightened. And I'm astonished at being here rather than there. For there's no reason why here rather than there, why now rather than then. Who has put me here, and by whose order and direction have this place and time been allotted to me? So the eternal silence of these infinite spaces frightens me. I can understand that reaction as well. So are we significant? That's a question you have to think through for yourself. I would say that perhaps our significance, and maybe I could say purpose here, our significance is apparent not from our place or time span in the universe, but from our existence at all. A product of the universe, or even perhaps a multiverse, that's evolving toward life, and our consequential ability to contemplate good and evil and react to it, and our place and purpose in the universe. And that's what I would posit to you today. So who are we? I need to close here. Carl Sagan says, we find that we live on an insignificant planet of a humdrum star, lost in a galaxy, tucked away in some forgotten corner of a universe. I know you can feel that way sometime. But the psalmist thought of it in a different way. And personally, I like this perspective a little better for myself. The psalmist in Psalm 8 says, O Lord, our sovereign, how majestic is your name in all the earth. When I look at your heavens, the work of your fingers, the moon and the stars that you've established, here's that insignificance. What are human beings that you're mindful of them, or mortals that you care for them? And yet you've made them a little lower than God and crowned them with glory and honor. You've given them dominion over the works of your hands. You've put all things under their feet. Now, the psalmist knew that people couldn't touch the stars. The psalmist didn't even know about galaxies, but somehow the contemplation was seen as dominion. And I would think that science falls in that perspective, that that being given the gift of understanding shows that we have a kind of significance based in humility that's been given to us, and I rejoice in that. So I think I will close. I just hope that you are also inspired by the universe as I am. There's much more to be inspired by. Space window at the cathedral, look at Psalm 19, and check out our dialogue on science, ethics, and religion for the American Association for the Advancement of Science. We have a lot of things going on, ongoing projects, lectures, and seminars, including our December 1st holiday lecture, which I think we're going to start calling the December Dialogue on December 1st. Stay tuned for that. We have a wonderful new website for resources. You can see at the bottom here, sciencereligiondialogue.org. Check it out on our general website up at the top here, AAAS.org/doser. And we're active on all these social media accounts. And then if you want to take a quick screenshot of some good resources that I can recommend to you, organizations and websites that I think are helpful to many people, go ahead and do that. Right now is your chance. And I thank you very much. And I'm looking forward to hearing what others have to say this evening.
Jennifer, thank you so much. You've taken us from the depths of the universe to the depths of our hearts, and that's really remarkable for a single lecture. I want to mention that 2 people in the Q&A have already said that it's 1 Corinthians 15:41, so they guessed it. I guess the awards go to Wendy Kreider and Grace Wolf Chase.
Oh, excellent. So they get extra credit. Okay.
That's right. They get a bonus. And one other thing I wanted to mention to everybody, just to the students in the audience, so they take some advantage here, is that Jennifer actually discovered a periodic comet when she was an undergraduate research assistant, and it currently bears her name. It's called the 114P Wiseman Skiff. So for those of you who think as undergraduates that work is unimportant, look how important it is. So thank you, Jennifer. Please enter your questions in the Q&A, and I will go on now and introduce our respondent for the day. So our respondent is Stephen Finnett. He has a PhD in biophysics from Syracuse University. His research involved there the neural network theory, and worked on also some visual perception work. He's done, when he moved on to be a research associate at the University of Arizona, Tucson, where he worked on classifying human breast tumors using a backscattered ultrasound and statistical pattern. He was then at Rutgers University, but now he's a research physicist in the acoustics division at the Naval Research Laboratory in Washington. His work there has been mostly on acoustical oceanography involving inverse source problems, ambient noise modeling, from the development of methods to include looking at environmental uncertainty in the ocean acoustical propagation models. He's a member of the Acoustical Society of America and the Union of Concerned Scientists. So we go from the universe to the oceans. Please, Stephen, it's nice to have you and to welcome you here.
Well, thank you for the introduction. I'd like to thank the organizers for inviting me to offer some brief comments on the very interesting presentation that we just saw. The universe is obviously a very inspiring and mysterious place. I never lost my interest in it. My comments will be based to some extent on my background and my own interests, but I do have a couple of questions for the speaker as we go on. With respect to contemplation of human purpose and our connection to the universe we inhabit, I think it's worth noting that everything we know or experience is acquired from a human-centric point of view. It's the only way we can acquire information of any kind. We don't often think of gaining knowledge in this way because it's so obvious to us. But I believe it's important to emphasize that it's the only frame of reference that we have to acquire knowledge about the world around us. In that sense, it's an inherently subjective question. As the speaker mentioned, it's more of a philosophical question. So any discussion of human purpose cannot be a purely objective endeavor in that sense. Having raised that point, let me delve a little bit deeper into what I'm trying to get at here. Our senses are the fundamental link and interface between the external world and our interpretation of what exists in the outside world, outside our bodies, in the universe itself. And our sensory systems are not perfect transmitters of this external information. In our lingo, they are what are called nonlinear detectors, meaning that they can filter, they can distort, they can compress the information in some way before our brain actually processes it. And different living systems actually sample different parts of the spectrum of information that are available to them. So they have a different perspective on the world around them than we do, obviously. So our brains interpret this imperfect information and recognize regularities in the external world that, after many, many centuries of study and analysis by physicists and other people, have allowed human beings to make sense of what we call external reality, i.e., the universe within which we are submerged, and which was shown in those beautiful slides in the presentation. And we understand these things in terms of a set of laws of nature that effectively codify these regularities. And these regularities, in turn, are developed from this inherently subjective point of view. But our minds are, in that sense, constrained by our own physiology, which is based on physical laws. So in some sense, we're constrained by our own atomic makeup, the stuff of stars that permeate our bodies, basically, as was mentioned. And hence, potentially limit our understanding of our purpose and connection in the universe that we're inherently a part of. So my first question to the speaker, of two questions I came up with, is the following. Does this limitation on knowledge acquisition as human beings serve as a fundamental constraint on our ability to fully understand the universe we live in and our connection to it? Or do you think that the information that's available to us is enough to fully understand the universe at some point in the future, maybe centuries from now, but that it's possible to ever fully understand what's going on? My own personal view is, as far as human purpose is concerned, I feel that we are the stewards of our local environment here on Earth and have an obligation to all life forms to protect it. But I don't see that there has to be any higher purpose for our existence. I fall in the Carl Sagan camp in that sense. Higher purpose seems to entail a faith-based argument that, as a secular humanist, I simply can't accept. My second issue here touches on our connection with the universe. One of the important unresolved issues in physics, in cosmology, has been raised, that is related to the fact that the universe and all of its properties are constrained by a few fundamental constants, such as the mass of a charge of an electron, the gravitational constant, other things like that. These things appear in physical laws and have been measured with great accuracy. If these numbers are slightly different than they actually are, on the order of, say, 1% or so, I believe, our universe would be very different from what we observe, and life as we know it, at least, wouldn't exist. So this naturally leads to a conclusion that the laws of physics in our universe seem to be fine-tuned for life to exist as we know it. So the question is, why is this so? Well, there's a school of thought based on what is known as the weak form of the Anthropic principle. It tries to answer this question by saying that the constants are what they are because we are here to observe them. It appears to explain why we see the universe in a certain way, but it doesn't really explain why the universe is the way it actually is. We really don't know the answers to those questions yet. It sounds a bit like a circular argument, but it raises interesting issues. Another possible interpretation of this concept is that constraints on human intelligence limit the type of universe that can exist to support intelligent life, and therefore our ability to interpret our place within the universe. Now, there are recent theories of cosmology that indicate the possibility and existence of multiverses that Jennifer mentioned for a brief time in her talk. And these multiverses are different universes that are thought, at least predicted to exist by some people. And each one of these universes has a different set of laws of physics and associated parameters. that govern them. The postulated existence of these multiverses seems to allow one to explain our existence by an argument using this anthropic principle in some sense, by saying that all the universes that are out there, and there are theoretically many of these, we happen to occupy the one that has these constants, these particular set of constants, and therefore we are here to observe it. But since we cannot experimentally verify the existence of other universes, this approach leads to a theory or a worldview of why we are here that can't be falsified. In other words, it's a theory that you can never prove to be false if this is the case. So my second question, if you care to answer it, is whether you consider this anthropic approach to understanding our place in the universe as a form of metaphysics or philosophy lying outside the domain of physics proper, or whether rather that it actually lies in the domain of physics. So thank you for allowing me to comment, and I'll turn the discussion back to the moderator.
Thanks so much, Stephen. That was really great. I think what we'll do first before we get to the questions in the Q&A is give Jennifer the chance to make any comments back that she wants to Stephen's comments.
Sure, thank you, Stephen. Those are really insightful questions and comments, and they're right on target. So thank you for sharing those thoughts. I think the fine-tuning business is interesting, but it's not something that I put a huge amount of weight on in terms of trying to determine something very profound about our being here as we are, our existence. It is true that there are fundamental constants that seem to be very sensitive in our universe, that if they were slightly different, the universe that we live in would not have evolved as it has, with stability, with stars forming and staying stable long enough for generations of them to come and produce the heavier elements that enables the production of planets, that enables the development of life, and so forth and so on. But there are others, physicists, who are taking another look at that and saying, well, actually, maybe these fundamental constants have a wider range than we thought, and you could still end up with a stable universe, and this is not my field of expertise. I'm just personally not willing to place my entire philosophy on whether there's purpose in the universe, as to whether the universe that we live in must have been fine-tuned to these exact parameters. I'm not willing to even place my theology on that. I learned about fine-tuning, long into my scientific career, and I think it's an interesting concept, but I don't think it should be held as something very fundamental, either to the physics perspective nor to one's philosophical or theological interpretation. That said, I also would agree that we can't, at least at this point, physically verify whether there are other universes that might have different fundamental constants, so that, as you say, we just happen to be in the one that has produced us, and so therefore, of course, we're here because we're here, and we're here because the constants have produced in this one universe the conditions that we need to have life. So as you say, the constants are what they are because we are here to observe them. So yes, it is kind of circular, in some sense obvious, but the question is, should you make something deeper about the existence of this kind of fine-tuning argument to point towards some greater purpose for the universe? And that I think is another philosophical choice. I look at it this way: even if there are a zillion universes and we just happen to be in the lucky one that has the constants that have enabled life that can have this conversation to occur, I still have to ask the question, why is there a multiverse that allows the possibility that one of these universes could exist that has the fundamental constants that allow advanced life to develop, that allow us to have the conversation that we're having. So you see that there's always that kind of further step back, and I'm still, you know, incredibly amazed that we can contemplate ourselves. In a sense, it is the universe thinking about itself and getting to the point, evolving to the point where the universe can think about itself. Not that every particle in the universe is what we would call classically alive, but the fact that we're part of this universe, we're as Jill Tarter pointed out, we're interactive with the universe, and we can have this contemplative state of mind. That to me is profound. And I think it's also profound that we can recognize that there are things wrong in the universe. There are things wrong on planet Earth. That to me, as a Christian, is almost the most compelling thing at all, that we recognize our evil and things that are not right. Things, I mean, I don't even have to go into detail. You can look around the world and see things that we react to because we know that they're not right. We can look into our own hearts and minds and sometimes see things that we know are not quite right. So where does that come from? That fits personally into a worldview that the Bible speaks to, of a kind of fallenness from the fullness that we could be and should be, and that we need divine help for that restoration to fullness of life. Now, that's not a scientific principle. That's not something I can glean by looking deep into the universe, but it is congruent with what I see around me. I've forgotten your other, your original point was, are we constrained by our own observational biases? Of course we are. Yes. So, but we don't even know, because we are in our own, we're limited by our own perceptions. We can only be a little bit objective. I mean, we try to be objective as scientists, but even science, we now know, is not, there's no such thing as purely objective science, because every science is done by scientists, and scientists are part of cultures and part of histories, and carry along with them certain worldviews and expectations that come from that cultural and even biological heritage. So I think that we're obviously constrained by our limitations, and we don't even perhaps see, because we don't have, if you will, God's eyes view. We can't kind of get out of ourselves completely. But I'd be interested to know how you view that as a scientist as well, how we can, knowing that we can't completely leave our observational biases, how we can still be satisfied with the scientific progress that we do make. So those are my immediate comments, Stephen. Thank you for your constructive and very insightful remarks.
Thank you both. I mean, Stephen, I'll give you the chance if you want to make any comments. If not, we'll go on to the questions. Stephen?
I tend to agree that the anthropic principle is not shared by everybody, and there are other ways of looking at the problem. I do think, though, that because we're limited by our own biology, the question arises, I guess not really thought of very much, as to what are our limitations in terms of understanding the universe around us. I mean, we've made remarkable progress just by looking around us locally in our local macroscopic world and extrapolating that information out to the cosmos. It's amazing that we have the ability to do that and accurately get a sense of what's going on out there. And the ultimate questions that might be raised, like what is the origin of the universe, or maybe what came before the universe, perhaps our minds are not capable of making headway in those areas because of our biological limitations.
Yeah, that's a very good point.
Okay, thanks to you both. Jennifer, there's some questions for you, and there are lots of kudos for giving a really great talk. I'm not going to read all those, but you know, there are a lot of people are very pleased with what you had to say. Okay, first question from Jay Atkinson. Assuming we can think of gravity in some circumstances in particle form terms as mediated by gravitons, How is the escape of gravitons from a black hole understood?
This is way beyond my my expertise, but it is a wonderful experimental challenge and a thought experiment as well. So you know, we have forces, we have fields, and we have particles, and how they interact is fabulous and mysterious. And I'm not even going to attempt to go to this, but if Stephen has expertise in this, I welcome you to respond.
I'm sorry, I missed the question there.
It's the very first one in the Q&A. Says,
assuming that we think of gravity in some circumstances in particle forms as mediated by gravitons, how is the escape of gravitons from a black hole understood?
Well, that's beyond my level of expertise as well.
Okay, so that's one that we'll file away for future thought.
Okay.
Okay. But I will say this, it does say, you know, things are always changing in our understanding. So the original thought that nothing can ever escape from a black hole, well, now we know that's not true in general, and that material can actually escape from black holes because of quantum uncertainties and things. As in terms of gravitons, which may mediate gravity, I would need to do some homework myself before I can address that. But thanks for the good question.
Okay. Next is, in your scientific opinion, what is the probability that there is life outside of Earth?
Oh, that's a rich question, and it's such an alive question because things are changing so rapidly right now in this field of finding exoplanets, and in this new field called astrobiology, which is bringing together the knowledge of what used to be siloed fields of science: astronomy, geology, space physics, chemistry, biology, astronomy. So what we're finding is basically two findings that are somewhat competing against one another. One is that planets are very common. Missions like the Kepler Space Telescope and some telescopes on the ground have found thousands of these exoplanet systems outside our own solar system. And then by doing the kind of extrapolation, we now realize that most stars have at least one planet, and that there are many, many planets in the habitable zone of their parent star, meaning they have moderate temperatures. And we're now building developing ideas for the next generations of telescopes that will be able to do even more detailed analysis of the atmospheres of Earth-sized exoplanets and finding out whether they show signs of biological activity. So we may be able to answer soon, I mean within the lifetimes of some of the people in this audience, whether there is strong evidence for biological activity outside of Earth. Now, by that, I'm talking about maybe evidence for things that are very simple life forms. I'm not putting my bets on whether we will ever actually be uncontestedly visited by advanced aliens, but so it's exciting. I mean, we're actually at the point where it's not going to be just science fiction, where we're actually going to answer questions about whether there's likely biological activity on some exoplanet, and that's really cool. And there's so many planets and so many possibilities that it almost seems inevitable that life must be in other Earth-type planets. Why not? And in fact, part of me feels that that's a natural, robust component of the universe that fits not only with my scientific expectation, but it fits well with my theological view that the Earth is rich with life. Then why not the whole universe rich with life? So I hope and expect that the universe is filled with life. Whether or not we find it, that's harder, because we have to have the tools to look out and look through a lot of planets, many of which will not be harboring life, and discern the ones that may be. But whether it's actually there is another question. And the counter to this is that it looks like many star systems are not hospitable to life at all. In fact, even in our own Earth's history, we know we've been clobbered by asteroids, which have changed the course of the development of what advanced life looks like, at least on planet Earth. It may be the case that many, many stars that have planets, but their stars themselves are very active with flares, and these flares can basically kill life on the surrounding planets and keep it from having the stable time to create an advanced stage. We know that a lot of environments are simply hostile to life as we know it. So I think the case can be made that life might be difficult or maybe impossible to get started. I mean, you can never say that there's no life anywhere because we can't look everywhere, but I think these are competing concepts right now, and we don't know exactly which direction it's going to go. But I do think that there's a lot of consensus amongst science enthusiasts that we need to look, and that's what we're doing right now.
Great, thanks, Jennifer. Next question is totally different vein. To add to the wonder, we have the consciousness to behold. That consciousness came out of matter itself, made of stardust, or it happened the other way around, or both followed from something different, who knows? Could you speak about consciousness?
Oh, goodness. I can speak about it, but I wish I could speak intelligently about it, which I don't think I can. But consciousness is a feature of life that I don't think is fully described yet, even by those who study it professionally. What does it mean to be conscious? How do you know if an entity is conscious or not? How do we know that we are conscious? And what does it mean for an entity to be conscious? Can we say that the universe is conscious because components of the universe are having the conversation that we're having? Or are subcomponents of the universe conscious that are self-aware? And what is the difference between consciousness and being self-aware? Is that the same thing? And that was an interesting way of putting it. Which comes first? Does the stardust come first, and then our brains come out of that, and our brains have developed to the point of being conscious? That's the way I, typically think of it. But is there some sort of, reverse order, that there's a consciousness first and then the stuff? And so I don't really know the answer to that, but I know that that's a really very interesting question. And I do think, in my view, that's sort of beyond just the science observations, but as I kind of see a universe that seems to have progressed toward the point of enabling self-aware life that can contemplate its own purpose and even be aware that it is conscious, that to me speaks to perhaps a pre-existing consciousness that had this all in mind. Now, that's not a scientific conclusion. That's, I think, a philosophical or religious conclusion, but that to me is congruent with what we see scientifically. But others may come to different conclusions. In fact, I'd be interested to know what Stephen has to say about consciousness.
You just took the words out of my mouth. Okay. I was going to Stephen, because he's worked in neural networks before. Stephen, do you have any comments on it?
Well, my PhD actually was involved with neural networks and problem of visual perception back in the 70s, in the last century, way back there. And things have evolved quite a bit since then, but we still don't understand vision. And let me just mention consciousness is, I consider that to be the greatest unsolved mystery in science. I even consider it to be more difficult than the physical problem of understanding the origin of the universe. And the reason I say that is that we have absolutely, in my opinion, no framework within which to really study this problem, because we're studying something which is purely subjective. And scientists, by their nature, try to look at problems objectively from the outside looking in. But in terms of consciousness, you're looking inside out, so to speak. And I don't think the tools have been developed yet in order to really get a handle on what this means. I look at it as a form of emergent phenomena, which is related to neural networks and their interactions. But how consciousness actually emerges from that is something that I've thought about quite a bit, but I really don't have a good answer for it. It's one of those great unsolved problems, very mysterious.
Great, thanks, Stephen. Next question, and I think this is for Jennifer. What are your thoughts on an emergent God pulling us toward love as social intelligence like us become more complex and can't really survive without attracting to a love-dominated universe, summed up perhaps in Samuel Alexander's phrase that the universe wasn't created by God, but has a tendency toward deity.
Well, okay, so here we get back to the point where I am an astronomer, not a theologian, and not a philosopher. But I do think that even as a Christian, as I consider myself to be, there are ways that have framed God and even interpretations of scripture as kind of this magic wizard that waved a wand and created the universe, or even created the forces that have developed into the universe as we know it, but is not this kind of interactive deity that we are growing more and more like and growing more and more to understand. And so I think that some of our understanding of the universe can and should mature our understanding of God. Now, whether it changes whether or not one's concept of an external God, or a God that is an entity or a personality or this kind of thing, I think that's beyond science, of course, and that's something that people have to look at individually as to whether what we're seeing in the natural world is congruent with certain pictures of God or not. And people come to different conclusions in that. I would have to think more. I mean, I like the idea of a love-dominated universe and that we're being drawn to it, but I would have to read more of the actual propositions along this line before I could say something along that line. I will say that one of the very basics of Christian faith is that God is love. In fact, Scripture says that, and yet that doesn't take away in any way the fact that God speaks, that God interacts, that God is responsible for the universe, that God is holds us responsible and things like that. And yet somehow all of this is coming from being described as love. So there's a lot to do with that. There's a lot to think about there. And I'm constantly thinking about that. And one of the things I think that can result from that, whether or not one shares that particular faith perspective, but is this idea of using our lives and the gift of life in service to others. And Stephen said that one of the things he thinks is our purpose is actually doing good for the inhabitants of the planet. And that, I think, is an outworking of love as well. So I will leave it at that.
Jennifer, thanks. I'm going to ask one more question, but it sort of is a wrap up of two questions that talk in a way about the limits of science, okay? So one asks, do you think the laws of physics only exist at low scales? Could there be solid laws of physics which apply at a social level or higher, which are not visible at a billiard ball level? And the other one asks about our understanding of nature and how we think about nature, and would it be possible if we could observe mental phenomena or even religious phenomena and consider them to be scientific if the methodology were scientific?
Okay, let me try to take the second one first, which is people have tried to do this and continue to, but it's just depends so much on what you consider scientific, and that even that terminology changes over time. And so, people have done experiments on whether people that are in deep religious meditation have changes in their brains, or whether, prayers actually change things or heal people, and I'm a little wary of some of that. I know some of it's been done very conscientiously, but it is, in some sense, it's stating the obvious. If somebody is in some kind of meditative state, of course their brain's going to look different, but that doesn't necessarily speak to whether there's an external reality of the spiritual realm in which that person is believing. So, And then whether or not prayers get answered in measurable ways, well, that even defies the prescripts of some of these faith traditions that say, don't put the Lord your God to the test, or that the Lord answers things in different ways that aren't necessarily what we would measure. So a lot of that, certainly think we can see evidence of people's psychological reactions to religious belief. Some of it's positive, some of it's negative. You can certainly see some of the impacts, but science is really a wonderful tool for measuring things that are in the natural world, where we can measure biology, we can measure the brain, we can measure the stars. But some of these questions go beyond what the tool of science is, I think, very good for. The other question, which is on whether there could be laws of physics at other levels than is traditionally considered. I would really need to see
social level or something even higher than that.
Yeah, I don't. I'd need to know more specifically about what that question is addressing before I could answer that, because I don't know. To me, laws of physics are the ways the natural world works at every level, from the quantum level all the way up to the macro level. And of course, social interactions and things involve both the micro and macro level of physics underlying our brains and our biology and all of that. But I would need to know the specific question. But I would also like to know if our physicist here, Stephen, has any comments to that question as well.
I think what he's getting at is whether there are laws of nature, basically, not necessarily basic physics, that one can use to describe psychological behavior or interactions among people, things like that, social level and higher. And I don't think that physics per se is the way to approach that problem. There are many people who apply mathematics to psychology and crowd behavior and things like this, but they don't use laws of physics per se to do that. Those are low-level laws, very fundamental reductionist laws. And I don't think it's really appropriate to use them, even though I do believe that social behavior has to be consistent with the laws of physics, because we are atoms, we are made of stardust, as you said earlier. So I'll leave it at that.
And of course, there's Murphy's Law, right? If anything can go wrong, it will go wrong.
It will go wrong. Yeah. Fortunately, that didn't happen in this session. So I want to thank both of you for a really fabulous session. This is incredible.